You know, fireflies are drawn to light. In the dark, the brighter one naturally attracts the others. Like fireflies to a flame, it's a simple instinct. Such magical creatures, aren't they? Interestingly, that same behavior can be turned into a mathematical algorithm for solving optimization problems. So today, let me show you such meta-heuristic method, the Firefly Algorithm. Well, ever heard of the Firefly Algorithm? Let's see. Imagine we want to find what is the best solution to some problem. Mathematically, we usually write it like this. Maximize f of x for all x in R to the d. Here, x is a vector of variables, f of x is the objective function, and R to the d is the d-dimensional Euclidean space, or the domain of the objective function. Our goal is simple. Find the value of x that gives the best value of f of x, or in this case, the maximum. If we want to minimize the objective function, we simply turn the problem into maximizing minus f of x. In doing so, the value of x that maximizes minus f of x will correspond to the minimum of the original function. But searching for such solution in the entire domain directly would definitely take forever, especially if the objective function is difficult to visualize. So instead, we send out a swarm of fireflies to explore it. Each firefly represents a candidate solution. If the firefly is at position x sub I, then its brightness, or light intensity, denoted by I, is determined by the landscape of the objective function. So, the better the solution, the brighter the firefly becomes. Naturally, the dimmer fireflies begin moving toward the brighter ones. However, this attraction depends on their distance. Two fireflies far apart can barely interact with each other. So first, we must measure the distance between firefly I and j, which is represented here. More explicitly, we use what is called the Euclidean distance in the domain space. Of course, the light emitted by fireflies fades with distance. Therefore, the attractiveness between fireflies is modeled as this equation right here, where beta sub 0 is the degree of attractiveness at zero distance. Gamma is the parameter that controls how quickly light fades. And r is the distance between fireflies. Thus, attractiveness decreases exponentially with distance. This means that nearby fireflies strongly influence each other, while distant ones barely interact. With this, we have the general idea of how the firefly swarm optimization works. This algorithm works by iteration, meaning each step t moves the fireflies towards the more and more optimum solution. More precisely, at each iteration step, if firefly I sees that firefly j is brighter, it will move towards it. This movement follows this rule. Let's break it down. The left term is what should be the firefly position in the next iteration. For the right term, the first term is its current position. We add this term with velocity, or the change in position over one iteration. We previously discussed that this term moves the firefly toward the brighter one, while this difference is the direction vector between the fireflies. However, we still have one major problem. In optimization, there are two types of optima, the global optimum and the local optimum. An objective function can have many optimum. However, only one is the global optimum, the best possible solution in the entire domain space. In other words, it is the vector of solution that gives the maximum value of the objective function. The local optimum, on the other hand, is the best solution within a certain limited neighborhood. If you think of the objective function as a plane with many valleys and hills, each hilltop is a local optimum. But somewhere far, far away, there might exist a much higher peak. That is our global optimum. That is why we must include this final term, which introduces randomness, drawn from a probability distribution, and scale with the step's i's parameter alpha. This randomness is important, since without it, fireflies will always move toward their brightest neighbor, and eventually might get stuck in a local optimum and stop searching for a better solution. When many fireflies interact like this, the swarm slowly reorganizes itself. This is the complete Firefly algorithm. Now let's look at an example with a multivariate objective function. We generate an initial swarm of fireflies. With our algorithm, we let dim fireflies chase the brighter ones. As clusters begin to form, the better solutions will attract more fireflies. And gradually, with each iteration, the entire swarm gathers around the global optimum. Finally, we pick the best firefly as the approximation of the optimum. And there we have it. So, to summarize, the Firefly algorithm is built onto simple ideas. Firefly's brightness represents the solution quality, and attraction between fireflies will move the swarm into the optimum solution. Or something like that. From afar, it looks like a swarm of lights drifting through the dark. But in truth, they are solving an optimization problem together.
Like fireflies to a flame, brightness begets attraction. I will search for myself
until everything
swarms
to convergence!